Okay, so let's start. Today we're welcoming Yann Bramoullé from Aix-Marseille University, and he'll give us a talk about who gives, who cares. I'll just tell you, Yann, that we're watching it together. So in this room there are a couple of people. I don't know if you can. Well, now the camera is on, so you can see only me. And we have some other participants online, those who couldn't join us. So go ahead.
Okay, thank you very much, Yevgeny. I hope to be able to come at some point. I was in Jerusalem once for the economic theory summer school. It was a fantastic moment and memory. Loved it. And okay, so this is a joint project with Raoul Deb and Ludovic Renou. Raoul is at Toronto, Ludovic is at Queen Mary. And don't hesitate to interrupt me anytime you want. So ultimately, what we're interested in understanding is informal transfer between people and households. So informal transfers are essentially transfers in cash or in kind, which are not market transactions. So it's about gifts, helping others, informal loans, this kind of things. Informal transfers play at least two important roles in our economies. They help redistribute income between rich and poor, so informal redistribution, and they help smooth consumption. Informal insurance. So for instance, one very well documented kind of informal transfer is remittances, the money that migrants send back home. And we know that for many poor households in many poor countries, this is the main source of income. We also know that it's macroeconomically important. So for instance, Haiti, which is a country with a big diaspora, and of course it's related to the diaspora. Remittances represent between 25 and 50% of GDP. Okay. And moreover, in Haiti, following the 2010 earthquake, there was a 20% surge. So remittances respond to shocks. Even in rich countries, these financial transfers are quite important. For instance, the numbers I could find for France, I don't know for Israel, but it's estimated that in France, financial transfers within families went from 2 to 4% of GDP following the 2008 financial crisis. So, giving money to children or grandchildren is one thing. Giving time is another super important type of informal transfer. And for instance, 50% of grandparents in France take care of their grandchildren. And this, of course, has this kind of, family arrangement has important implications, for instance, for the labor supply of women and things like this. So these informal transfers are important, and economists have been working on them for a while. And of course, a very important kind of obvious but important fact is that they flow through family and broader social networks. And there is a growing empirical literature that documents the network features and patterns of these transfers and helping relationships. So for instance, Marcel Fachan at Stanford is one of the researchers that has been, pioneering this empirical literature, but it's not the only one. And just to give you a concrete example, here is an example. Here is a network describing informal lending and borrowing relationships between households in a village in rural India. This comes from the Banerjee, Chandrasekhar Duflo-Jackson project. We don't see it on this graph, but it's, of course, this kind of relationship is correlated with subcaste in the Indian context, but it's not a one-to-one correlation, right? So you have cross-caste relationship and So that's the kind of data empirical people in the field are collecting these days and trying to understand. Now, an interesting recent change has been induced by the widespread adoption of mobile phone in poor countries. So it was estimated a few years ago that over 1.7 billion people now own a mobile phone, but no bank account, right? So for instance, especially in sub-Saharan Africa, most people now have a phone, but the bank system is still totally underdeveloped. And an interesting aspect of this widespread phone adoption is that companies have been developing phone-based financial services. And in particular, I started with airtime transfers, so the ability to send, airtime like minutes, phone minutes over the phone to other people. And then it was transformed into actual mobile banking, so the ability to send money by phone. And there are some interesting recent studies on this. This paper by Blumenstock, Eagle, and Sachson, which analyze the universe of calls and airtime transfers in Rwanda before the adoption of mobile banking, and where they find that, and they document that airtime transfers flow to people affected by disasters. And perhaps more important is this Jack and Suri AER paper, which documents the widespread adoption of mobile banking in Kenya, and who show that users of this mobile banking app, M-Pesa, are better able to smooth consumption than non-users and receive transfers from a wider network. So one important aspect of this mobile phone banking is that the transaction cost of sending money are much lower. It's much cheaper, right? Because like classical things like Western Union, and they take a relatively high fee for sending money, but it's much cheaper with this mobile phone app, which has a first order impact on these informal transfers and the way people help each other. Now, that was for the empirical part of my talk. In parallel to all this, empirical literature and connection of, data and transfers in the field, there has been a growing theoretical literature developing models of informal transfers in networks. Okay, so taking the network aspect and dimension seriously. In the recent literature, there are two main strands that I want to highlight today. One is this these papers on risk sharing under network constraints. So in particular, there is this very nice Ambrus, Möbius, Seidel AER paper, where here, and a more recent paper by Attila Ambrus and Gao and Milan, where here the idea is to start from a risk sharing model and to add network constraints on top of it. I can tell you more if you're interested on this approach. That's one approach. Another approach on which I've been working for a while now, and the paper I'm presenting today is related to this, is to analyze models of altruism in networks. So model where people have altruistic preferences, they care about, other people disconnected.
Yes, I'm not sure either, but you're here again.
Okay, let's hope that, it won't disconnect again.
Yeah.
Okay. So in this other strand on which I've been working, people have altruistic preferences, they care about others, and they give each other informal transfers because they're altruistic. So I've been working on analyzing the model, and I will tell you more about it. We had a first paper in Econometrica on this, and then in a second paper we looked at the risk-sharing aspect of these altruistic transfers. However, at this stage, there is still very little research trying to combine theory and data and trying to understand how to get these theoretical models to data. So what I'm presenting today is related to this research program. It's kind of a first step in understanding the testable implications of these network models. So what we do here more precisely is to analyze the revealed preferences of these models of altruism in networks. In other words, we will suppose that a researcher observes transfers over several rounds of informal transfers in a population. So the kind of data I have in mind, we don't have an actual empirical application yet, although it's our objective to do it. Hopefully, you know, in the final version of the paper, we'll have one. So we are kind of looking for data now. But the kind of data we have in mind would be administrative data from this mobile phone app in Kenya, for instance, where you have, you know, very precise disaggregated micro information on, you know, who gave, who sent money to whom, when, and how much, but not that much information of the individuals themselves and their situation and income and stuff. And the question we're asking is under what conditions would this observed transfer be consistent with the Nash equilibrium of the model of altruism in network? Under what conditions can they be rationalized as, you know, equilibrium transfers of the model? So that would be kind of our main questions. And results in the nutshell, essentially will show that first the model is refutable, which is not obvious a priori, but there are, you know, transfers that are observed transfers that are consistent with the model and observed transfers that are not. The model is refutable. And we will provide three characterizations that are equivalent, but kind of, I mean, which, as you will see, different mathematical statements. One will be a set of affiliate conditions. So the observed transfers will be consistent with the model if and only if a set of linear equalities and inequalities have a solution. Then we'll have a characterization related to the network structure of the observed transfers, and more precisely to properties of oriented cycles in this transfer network. And finally, we'll have a characterization which is more economic, which will be related to the fact that the transfers we observe, as we will show, reveal information on the relative strength of the altruistic relationships among different pairs. So this will be, you know, three necessary and sufficient conditions. And we will also provide sufficient conditions related to kind of simple geometric conditions on the transfer network. Okay. A word on the literature. So essentially, we contribute to three literatures. First, there is an old but still active literature on the motives behind informal transfers, with ongoing debates. Why do people help each other? Is this altruism? Is this exchange? They're in reciprocal, you know, risk-sharing agreements, for instance, informal agreements, or is it social pressure? So there is a big literature here. I put a few references, including recent references. There are some recent interesting work with clever experimental design to get at these motifs. Essentially, most of this literature does not take the network aspect of the transfer into account. And we show that this network, you know, the network patterns of transfers actually have some informational content that can help get at the motifs. There is a big literature on network games now. I've been involved with this literature, I mean, since my PhD. And we're starting to see the first structural estimations of network games. In particular, Marcel Fachan has a recent working paper with Simon Hess, who is now in Vienna, where they do a structural estimation of a variant of the model of altruism in networks on survey data on Gambia. This is nice. We're related to this literature, as you may know. I mean, more or less every time you do structural estimation, you impose a lot of parametric restriction. By contrast, the reveal preference approach we're working on here is essentially non-parametric. Okay, so it imposes much less, puts much less structure on the model. And of course, the cost, that's the benefit of doing reveal preference is the cost is that you can say less, but you can still say things on in particular on the shape of the altruism network. And finally, there is a literature on reveal preferences that is still active. One remark is that, and I was not super familiar with the recent literature on this. My co-authors are contributors to this literature, and I was quite shocked to learn that there is very little on reveal preferences and games. Seems such a natural, combination, but there is very little. I mean, I can speculate on why, but here we have a reveal preferences approach in a strategic context. So we're contributing to that small, literature. And moreover, it's the first application we know of the reveal preference apparatus to a network context. Okay. Any question on the big picture before I dive into the math and the models? No, that's fine. I mean, don't hesitate. Okay. So the model. So it's a static model. Every agent has some initial income and may give tau ij to any other agent. So the matrix tau collects all this tau ij. It represents the network of informal transfer. In this version of the model, there is no transaction cost. And because it's static, the final income of an agent is the initial income plus the transfer fee received minus the transfer he gave. Okay? So it's in this model, aggregated income is conserved. There is no transaction cost. And transfer redistributes money in the population. Now, we are assuming that agents have altruistic preferences. And here we're considering a benchmark kind of simple model of altruism, which was actually the first model studied by economists, introduced by Gary Becker in his 74 social interactions paper. So people have some altruistic utility VI, which is a linear combination of private utilities of income. So UI is a strictly increasing and differentiable function of income. In the direct analysis of the game, we assume that it's strictly concave. For the reveal preference approach, we don't need this, but think of it as being strictly concave. And then alpha ij is a bilateral parameter that captures how much I cares about J's private well-being. Okay, so if alpha ij is 0, I does not care about J, and if alpha ij is high, I cares a lot. We are assuming that alpha ij is strictly lower than 1, so you cannot care more about someone than you care about yourself, someone else. And it's actually an important assumption for what we are doing. So all these bilateral altruistic coefficients, they're collected in a matrix, which is, which represents a weighted network, the altruism network, which represents the structure of the social preferences in the group. Who cares about whom and how much? Okay. Now, these altruistic preferences and the transfers, this defines a non-cooperative game, where agents decide whether they want to help others and how much in order to maximize their altruistic utilities. And everyone is doing so at the same time. So a Nash equilibrium of this game is a matrix of transfers such that for every agent, conditional on the transfers made by others, the transfers I make maximize my altruistic utility. Okay. And clearly here there will be lots of network effects. If I care a lot about someone who is poor, but that person is being helped by others, I may not need to help him. Okay. If by contrast, I care a lot about someone, that someone cares a lot about someone else, and give her friend or her cousin, a lot of support, I might end up giving support to my direct friend. To give some, I'll show you an example right away. So, equilibrium conditions are pretty easy to derive here, right? So the cost, when I give $1, my income, decreases by 1. The income of my friend increases by 1. The marginal cost of giving is my marginal utility of money. The marginal benefit is alpha ij u prime j. So in equilibrium, if I give to someone, you must have this equality relation. Ui prime has to be equal to alpha ij uj prime. But then if I don't give, okay, I don't give only when the marginal cost is greater than the marginal benefit. So ui prime has to be greater than or equal to alpha ij uj prime. So for instance, with Cara utilities, we don't have risk at this stage, but we want to be able to introduce risk. So with Cara utility, the conditions you get is that are expressed here. And in words, what it means is that an agent never lets the consumption of one of her poorer friends become too much lower than her own, right? So yi minus yj, the difference in incomes is bounded from above here. With Cara utilities, you never let this difference become too high. If it's higher than this bound, you will start to give money, which will reduce the difference, and you give money until the difference is precisely equal to the bound. Okay, but of course this applies to every pair, and every agent is doing so at the same time. Okay. So in our first paper in Econometrica, essentially we analyze the properties of this game. If you're interested in kind of the direct analysis, I don't want to spend too much time on the direct analysis. I just want to show you one example and one result from this early paper. One example just to show you a bit how the model works here. Put 5 agents on the line and shock one extremity. So they all have equal income, but one, at the extreme right, one agent has 0. And consider Cara utilities and an altruistic coefficient such that the bound, the largest possible, the bound such that the difference in incomes of 2 friends cannot be higher than this bound. This bound is 1. So it's strong altruism, if you want, with respect to these income levels. So if you do one round of best response here, yeah.
There's a question here. Is it a potential game?
Yes, exactly. This is on the next slide. Exactly. And it's when we understood this, the potential property really helps in this game. We could derive many results in the direct analysis through this, indeed. Well, it's not an exact potential game. It has a best response potential. Okay. So with one round, you know, so you have this agent who has a shop, and this agent has one friend who cares about her. So with one round of best response, the agent with the shop is being helped by her friend, and this is, you know, the best response. So you get transfers such that the difference in incomes after transfers is exactly 1. Okay. Is this Nash? It's not Nash, right? Because now the agent who just helped his friend in need deteriorated the situation, and he has another friend who is rich who cares about him or her. So if you do a second round, he will be helped by his rich friend. Now it turns out, so you can do, you know, multiple rounds, and actually here you will need an infinite convergence is not finite, but it will, like myopic best response will converge. And in any case, there is a unique Nash equilibrium, which is depicted below, where you can see that we get kind of a propagation of shocks in this altruism network, right? People who are closer from the agent receiving the shock are more affected, but there is a distance in the network so that if you're far enough away, you're not affected. Okay. So this is a kind of thing that is going on in this model. Is this example clear?
Yes.
Okay. Okay. Now, indeed, it is a potential game, and one result we showed in the first paper is that so this is the best response. This 5 function here is the best response potential for this game. I mean, you can check that the first order condition of maximization of phi are precisely the same as the Nash conditions. And moreover, when the utilities are strictly concave, this potential is concave. So you can show that Nash equilibria are actually the maxima of this concave function. And it's nice because it means that finding equilibria here. Remember that here a strategy of a player is a vector of transfers. Okay, so we're in a high dimensional space. If we had to do, you know, fixed points, it would be super demanding. But you can do. We're in the domain of convex optimization, right? We just have to find the global maxima of a concave function. Well, it's still high dimensional, but it's easier. In particular, one thing you can show, which is, you know, kind of standard with potential game, is that sequences of myopic best responses converge to Nash. So that's one possibility. Another interesting aspect here is that if you look at this, so the potential has kind of a benefit and cost formulation, and the cost part is related to minimum cost flow, which is a classical problem in optimal transport. So this finding Nash here is kind of related to standard CS optimal transport problems. Okay. Okay. So this is about the model itself. So what we are doing in this new paper is doing the reverse analysis, the revealed preference analysis. In particular, we will assume that a researcher observes transfers over several periods in a fixed population. So again, think about this M-Pesa data. So who gave money to whom, how much, over several rounds. He may or may not observe incomes. We will have results for the two cases, but for instance, with the M-Pesa data, there is no data on income. Okay? There is very little data on individuals' situation. There is detailed data on transfer, but that's it. Now, we say that transfer data is rationalizable by this model if there exists time invariant altruistic coefficient and strictly increasing and differentiable time varying utility functions and time varying incomes, so that at every period the observed transfers are a Nash equilibria of the game. Okay, so we are looking at that's the usual approach with revealed preferences. Even though there are several periods, we are not doing a full dynamic analysis. We are doing, repeated static Nash. Okay. Sorry. If we also observe income data, which can be the case with surveys. Yeah, sorry, go ahead.
Why are you allowing the utility function to be time dependent, but not the altruism coefficient?
Right, good question. We can do everything. Actually, we don't have results for all the cases, but we can easily cover time varying altruistic coefficients and time varying utility functions. We have results for that. We also have results on, it seems the fact that utility can be time varying, is related to the fact that circumstances of the households or individuals can change. So they have a kid, for instance, between one period and another. Yeah. Again, you'll see in the results. Actually, if we don't observe incomes, assuming that utility is time varying or not, will lead to an equivalent characterization. That doesn't matter. Doesn't have empirical content in this context. Okay. Okay, so we will also think about situations where you observe incomes and transfers. And then we say that transfer and income data are rationalizable if there exists time invariant coefficients. But again, we can actually doing time invariant is a harder thing theoretically. Doing time varying is fairly easy. I'll tell you in a minute what we get there. Time invariant altruistic coefficient and time varying utility function, such that again, the observed transfers are a Nash equilibrium of the induced game, but now we corresponding to this observed income. Okay. Okay. Now, here is a very simple example of situation which cannot be explained by the model. One period, 1 gives to 2, 2 gives to 3, 3 gives to 1. Why do we have a problem here? Suppose that this is a Nash equilibrium of the game for some income. Then because 1 gives to 2, we must have this equality. U prime 1 is alpha 1 to U prime 2. 2 gives to 3, 3 gives to 1. Then what you can do is that you can multiply all these equalities. And when you do this, because it's a cycle, you will get the product of the marginal utilities of the agents in the cycle on both sides of the equalities. Okay. We did assume that utility was strictly increasing and differentiable, so this is strictly positive. We can just, it cancels out. And what we get at the end is that the product of alpha 1, 2, alpha 2, 3, alpha 3, 1 is equal to 1, which is incompatible with our assumption that it was strictly lower than, that each coefficient is strictly lower than 1. Okay. So as long as the coefficients cannot be equal to 1, this cannot happen in equilibrium. By contrast, if you remove one link here, there is no problem. Okay, it's really because of the cycles here in one period.
So it's working. I have a question. So essentially, it could be that some people are extremely altruistic, and or everyone is extremely altruistic there, and they care about you as much as they care about themselves. And then it seems that this falsifiability argument failed.
Yes, you're totally right. If the altruistic coefficient can be greater than 1, essentially anything is rationalizable. Okay, so all the results we're obtaining today, they're kind of a joint. It's a model joint with the hypothesis that the altruistic coefficient cannot be greater than 1. Okay. Okay. It turns out that with one period, you can fairly easily show that with one period, transfer data are rationalizable if and only if you don't have directed cycles like this. So if and only if the transfer network, the transfer graph, which is binary and directed, telling who gives to whom, is acyclic, doesn't have cycles. Okay, with one period. However, with more than one period, things are more complicated. So here is probably the simplest example of situation where with two periods, which is not rationalizable, but where the period by period graphs are rationalizable, but when you put it together with the two periods, it doesn't work. It's not consistent with the model and the assumption that the altruistic coefficients are lower than 1. So what's going on here? 1 gives to 2 who gives to 3 in the first period, and 1 gives to 3 who gives to 2 in the second period. Why is this inconsistent with altruism? So the key observations here, I'll show you the math in a second, but if we have a period where 1 gives to 2 who gives to 3, it has to mean somehow that 1 is more altruistic towards 2 than towards 3. Why is that? So suppose that it's a Nash equilibrium of the model. Write down the Nash condition: 1 gives to 2, 2 gives to 3. So we have these two equalities. And then let's not forget the inequality coming from the fact that 1 does not give to 3. So 1 does not give to 3, meaning that ui prime is greater than or equal to alpha 1, 3, u prime 3. Right, so remember, in the not giving here still tells you something. Essentially, if you look, for instance, at the Cara condition, if you don't observe a transfer between I and J, it has to mean that the altruism between I and J cannot be too high somehow. It means that the alpha ij coefficient cannot be too high somehow. Okay. So we are exploiting this here. And then I wrote the conditions precisely to be able to multiply the three conditions together. Everything is positive, so with the inequality, it's fine. And again, we have the product of the marginal utilities on both sides for all the agents in this 1, 2, 3 cycle. Cancels out, and what we get now is that the product alpha 1 to alpha 2, 3 has to be greater than or equal to alpha 1, 3. Somehow the indirect altruistic relationship between 1 and 3 through agent 2 has to be greater than or equal to the direct relationship, meaning that alpha 1, 2 is strictly greater than alpha 2, 3. Is the example?
I mean, Eagle asked you previously if what happens if the alphas depend on T as well. And it seems that it might change the result here as well. So,
Sure. So if the alpha, exactly, you're right. If the alpha are time invariant, are time varying, then essentially there is no bite to having several periods, right? If the alpha are time varying, the utility is time varying, a model is transfer data is rationalizable over several periods, if and only if in every period, independently, what you observe in this period is rationalizable. And then we know the condition. A single period transfer data is rationalizable if and only if the transfer graph is acyclic. Okay. So if the altruistic coefficients do not depends on time, there is no you just get independent conditions for every period. If they don't depend on time, however, if they're fixed, now you have this issue that what's going on in one period might be, and what's going on in another period might be inconsistent, right? Yeah. Typically, in the revealed preference literature, like the standard consumption 101 revealed preference GARP thing, typically researchers assume that things do not depend on time, and so you have several periods, but you're looking at a utility function which is the same across periods. Here we can do both. Actually, the condition again, the condition we get if the utility function does not depend on time and the altruistic coefficient does not depend on time is actually the same. It's a surprising property, but it's what's happening here as the condition we get when the utility function does depend on time. Okay. So in any case, to get back to the example, we see 1 gives to 2 who gives to 3 in period 1. This tells us that 1 is more altruistic towards 2 than towards 3. But then in the other periods, we see 1 gives to 3 who gives to 2, which tells us that 1 has to be more altruistic towards 3 than towards 2, and we get a contradiction. Okay. By contrast, there are many other examples which are perfectly rationalizable. For instance, 1 gives to 2 who gives to 3 in one period, and 2 gives to 3 who gives to 1 in another period. You can easily rationalize this kind of thing. Okay, so it's not totally obvious. So some patterns are consistent with the model, some are not. Now, let me introduce some definitions to get at the main theorem. Okay. So we introduce oriented cycles. So what are oriented cycles? So they're cycles which are set of different agents, and then the last agent is the same as the first. And each link in the cycle has an orientation, forward or backward. The links forward must be giving relationships in the same period. The links backwards are receiving relationships, and they can be across periods. So to give a simple example, in the 1, 2, 3, 1, 3, 2 case, for instance, one oriented cycle is 1 gives to 2 in period 1, 2 gives to 3 in period 1. These are forward links. 3 receives from 1 in period 2. The backward link. Another one is 1 gives to 3 in period 2, 3 gives to 2 in period 2, and 2 receives from 1 in period 1. Okay, so these are two oriented cycles that are built from the transfer data. Now, if you have a collection of these oriented cycles from the transfer data, you can count for every pair the number of times the ij link appears forward or the number of times it appears backward. These are my n plus and n minus counts. Okay. Now, an important observation is that if the data is rationalizable and transfers are Nash equilibrium of the model for some incomes, every time you have an oriented cycle like this, the links forward are revealed stronger than the links backward. What do I mean by this? And how do we get this? So essentially, it's an extension of the argument we did for the simple examples, but in general, you have a cycle. If you have a link forward, you know that ui prime is alpha ij u prime j if you have I giving to j. And because it's the same period, we have all this u prime of this period. And for the links backward, we just use the inequality of the Nash condition, which is always true in any case. Okay. And then we take the product. We have the product of the marginal utility of all the agents in the cycles on both sides. They cancel out. And what we get at the end of the day is that the product of the altruistic coefficients for all the links forward has to be greater than this product for the links backward. Okay. This is what I mean by reveal stronger. It tells us something on this product of links.
In the case of a backward link, why don't you have an equality?
So we have equalities related to the receiving relationships, but they're in different periods. And we want to, so the products will not cancel out, but we want to be able to have the same period for the marginality, the product of the marginal utilities to cancel out. Okay.
So the cycle concerns multiple periods. This is something I missed, probably.
In this definition I'm giving you, the links forward, they have to be the same period, but for the links backward, it can be different periods.
Cross periods.
Yeah.
I see. Okay. Okay.
Okay. So when I say reveal stronger, it means that the combined strength of the links, in the sense of the product of the coefficients, is larger, is greater than or equal to. Okay. Okay. Now, here is the main theorem of the paper. So, some transfer data is rationalizable with time-varying utilities. If and only if it's rationalizable with strictly concave time-invariant utilities. So when you only observe transfers, concavity has no bite here, and time-varying or time-invariant utilities is the same. If and only if transfer and income data are rationalizable for strictly increasing time-varying utilities. So if utilities are time-varying, observing income has no bite, doesn't change anything. So if and only if what? Any of these, so all these conditions are equivalent. The first condition is a set of Afriyat conditions. If you're familiar with reveal preferences arguments, you'll be familiar with these kind of things. So if and only if there exists some lambda IT numbers, Cij negative numbers, such that if I give to J in period T, then we must have this equality. And if I does not give to J, we must have this inequality. So to get at these Afriyat conditions, they're actually just the log. We get them from the log of the Nash conditions, right? If you just take log here, lambda 80 will be, the log of ui prime of yi in this period, and Cij will be log of alpha ij. Okay. Of course, what we gain by taking the logs is that now we have linear equalities and inequalities. So we're in the domain of linear programming. This is one condition. Second condition, the network condition, if data is rationalizable, if and only if there does not exist a collection of oriented cycles in the data, such that for every pair, the number of times the link appears forward is greater than or equal to the number of times it appears backward, with one strict inequality. Okay. Somehow the rationalizability here is related to this counts in oriented cycles. Okay, well, one condition. And finally, it's also equivalent to the fact that if you look at this revealed stronger comparison among sets of links, more precisely multi-sets, so sets where one link can appear several times, there is no strict cycle in this revealed stronger comparison. You cannot have a set which is stronger than another, which is stronger than another, and so on. So we a cycle in here with a strict stronger at some point in the cycle. Okay, so I skip this. A few comments on the proof. Essentially, the network condition of cycles and discounts, it comes from a variant of Farkas lemma applied to the problem. This I said before. And when you get to data and actually want to apply this condition, the one condition which is really useful is the Afriad condition, actually, because it's linear programming and it's pre-programmed in most software and it's fast. Now, one kind of important corollary, if you want, of the theorem that we didn't expect at first is that it turns out that in this model, only the directions of transfers matter, not the amounts transferred. Okay. Well, that's the property of the model. One interesting aspect of this is that it means that this revealed preference test is robust to measurement error in transfer. As long as this measurement error precisely captures, who gives to whom, if you don't have the amounts right, that's not a problem. Okay. And as we already, talked before, the assumption that alpha ij is strictly lower than 1 is critical here. If it can be greater. Yeah.
But this issue with direction of transfer, will that still be valid if you have some financial frictions? So if the sum at the beginning and the sum at the end of the y's is not the same?
So you're asking what happens if there are transaction costs?
Yes.
Good question. Short answer is I don't have a clue. Right. So if here I don't know. We haven't talked about this in this revealed preference context. In the first paper, we spent some time on an extension with transaction cost. Yeah, I don't know. That's a supernatural extension to think about, right? Because if you look at, for instance, remittances, you have transaction cost. Okay. For things like, money gifts between close family members, here typically you won't have money loss, but for remittances, people being far away sending money, you have transaction costs. Yeah, I don't know. That would be a nice paper to write, I guess. Right. The other kind of important thing to note here in this approach, if the data is rationalizable, if the transfer data you observe is consistent with the model, what you recover then is ordinal information on the relative strength between sets of leads. Okay, you won't recover point estimates of the alpha. That's not what's happening. If you want point estimate, this is where this is what people do when they do structural estimation. This is what's going on in the paper by Fafchan and Hess. But then you have to make strong parametric assumptions. So for instance, in that Fafchan and Hess paper, they're assuming that the UTT is a log. And then they're assuming some very specific stochastic process on the altruistic coefficient. Okay. We don't have any assumption of this kind here. And then you don't get point estimate, you will recover things like, well, alpha 1,2 is greater than alpha 1,3. Okay. One new result we're working on right now is we're trying to understand for a given network, what is the maximal information you can learn on this altruistic coefficient. If you can observe, any kind of incomes and shocks, what kind of information you recover. We know that there are cases where you recover the full ranking of the altruistic coefficients, and we know that there are cases where you cannot learn everything. But this is one thing we're working on right now. So this oriented cycles and quantity oriented cycles conditions a bit abstract. But one thing we could obtain from the theorem is a much simpler sufficient condition, which is related to this acyclicity I already mentioned. So consider the aggregate graph where you aggregate across all periods the information on who gives to whom. So it's binary, and there is a link between I to J if in some period I gives to J. It's a simple binary graph you can build from any transfer data. And one thing we can show is that if this aggregate graph is acyclic, then the data is rationalizable. Okay. If you don't have cycles, so here when considering transfers across periods, it's rationalizable. And we know that with one period, it's an if and only if, but not with two periods or more. With two periods or more, you can have cycles and rationalizability. This can happen. If it's acyclic, it works.
You showed an example.
Sorry?
You showed an example.
So in the example here, we do have
the 1, 2, 3. Yeah.
No, right? Because here it's an example where we do have a cycle, the 2, 3, 3, 2. 2 gives to 3 in period 1, 3 gives to 2 in period 2. So we have a cycle in the aggregate graph. But this one. But it's not rationalizable. Here it's an example with a cycle where it's not rationalizable. But there are situations with cycles in the aggregate graph which are rationalizable.
No, I meant the previous example, not that.
Sorry?
The previous slide was the example you wanted.
Yeah, right. So here, right. Well, here again, it's a situation where we.
No. The first one you showed, the 1, 2, 3, but not this one, but the other one, where it is rationalizable, but it is a cycle if you look at the aggregate, no?
This one, you mean?
Yes.
Yeah, you're totally correct. Okay, you're totally correct. Here indeed, the aggregate graph is one gives to 2, 2 gives to 3, 3 gives to 1 across periods. So we have a cycle and it's rationalizable. Totally correct. Okay. One implication in particular is that if you have a natural hierarchy, which could be related to income levels here, and transfers only flow from above in the hierarchy to below, then it has to be the case that the aggregate graph is acyclic, and in this case, it's always consistent with altruism. Okay. And something else you can show, which is not a direct implication of this acyclic property, but if the graph is bipartite, meaning that in every period, you only have giver and receiver. You have no one who both receives and gives, okay? Like the 2 in the 1 gives to 2, gives to 3. It's either you receive or you give. In that case, we can easily show from the theorem that it's also rationalizable, okay? There are some, somehow to get in constancy with the model, you need these intermediaries, people who receive and give. Okay. That would be an example of, bipartite graph. Here is an example. So when you start to have, several periods, it's starting to be not totally obvious to understand when there is inconsistency. It's not totally obvious to understand what's going on, and this is where the theorem, of course, becomes useful. Here is a kind of a minimal example of refutable data with 3 periods. And I don't think I will even try to give the intuition here. So we kind of, we found it by running simulations and stuff, but 1 gives to 2, we gives to 3. 4 is not in the part of the transfer here. 4 gives to 3, we gives to 2. 1 is not part, and 1 gives to 3, 4 gives to 2. Any 2 periods, if you just look at any 2 periods, it's rationalizable. It's really when you put the 3 periods together that you have an inconsistency. And you can easily build these examples where, everything with n-1 period and with k-1 period is rationalizable, but, with k period it's not. And here, so we can apply the theorem, and, you find that here you have 3 oriented cycles built from the data, and so that this counts, such that with the cycles, links appear forward more than they appear backwards, and strictly so in some cases, and that it cannot be rationalizable. Okay. And with one point here is that without the theorem and these conditions, it would be hard. Just staring at this, and it would be hard to know whether it's consistent with the model or not. Now, the last thing we do in the paper is to looking at alternative models. In particular, we look at the model of network constraint risk sharing of Ambrose-Möbius-Seidel, and we also look at a repeated game, so the dynamic version of our current model. And we essentially find that any transfer data can be rationalized by either model. So if you only observe transfers, these alternative models they don't have refutable implications just on transfer data. Okay. what I just said is not true if you observe transfers and incomes. And we haven't fully worked out what was going on in that case. Okay, I'm reaching the end of the talk. Some of the things we are currently working on now. So notice that this revealed preference test, they're binary. It's either consistent with the model or not. It's a general property of, revealed preference arguments and conditions. However, it's not totally satisfying because, and people researchers in the revealed preference literature are actually working on this more generally to develop statistical framework where, rather than having a 0-1 rationalizability condition, you would want to have a probability, for instance, that that data are consistent with the model. Okay. To do this, you need to introduce error terms, possibly related to measurement error, for instance. That would be one way, although in our case, it might not help much, but and to do things a bit differently. We do want to get this to data, so we are currently talking with empirical teams working on the topic. A broader issue here is that one thing that is missing in the literature, so we have these different motives for informal transfers. Altruism is one, and there is evidence that altruism matters, but it's not the only one. There is this big literature on mutually beneficial self-insurance arrangements, for instance, so exchange is another motive. And there is also a lot of recent evidence that social pressure is a big motive here as well. In many situations, especially in poor countries, but not only there, people give to others because they feel obliged to. If they could avoid giving, they would prefer, but there are social norms, right? If you're successful and rich, and your cousins ask for help or money, kind of have to give. So at this stage, we have network models on altruism and risk sharing, but what we don't have would be models accounting for all the possible motives and leading to possible identification and estimation of what the strength of the various motives and which matters when. I know of only one empirical paper by Rosenfach and Stark that combine altruism with informal risk sharing, but I think there is much more to do here, looking at different motives. And that's it for me.
Thank you, Yann. Any questions?
Yes, I have one question. You start with quantitative data about the size of the transfers, and then it turns out that you don't care about the size of the transfers, presumably because you can always choose the size of the altruism coefficients to fit the data. Could you take the opposite approach, so to speak, start with qualitative data about who transfers to whom, and then restrict yourself to altruism coefficient, which is, say, either 0 or 0.5, and then rationalize some transfer with these quantitative features? Is my question clear?
I'm not totally sure I understood fully. So what's going on here is that it's not that we don't care about the size of the transfers, right? It's actually a property of the model. One result we're showing here is that, in other words, if you take two transfer data, which have different amounts transferred, but the same, you know, who gives to whom, this is the same in the two data, then, you know, either they're both rationalizable or they're both inconsistent with the model, right? So rationalizability does not depend on the size. It's a property. It's not that we don't care, right?
Yeah, I understand. This is a result, not an assumption. So here's my question.
Yeah.
Suppose you restrict yourself to altruism coefficient, which is either 0 or 0.5. And then you are given only the network of who transfers to who. Are there sizes for these transfers which are rationalized by these very specific altruism coefficient of 0.5?
Okay, I see. Good question. I think the techniques we developed here can be used to answer your question, right? Because essentially, if we have actual transfer data, when we can get out of and suppose it's consistent with the model. If it's inconsistent, it's inconsistent. Okay? Suppose it's consistent with the model. Then what we can get from these oriented cycles and stuff, we will get a series of ordinal ranking between sets of links. Okay. So from the data, we will extract information on which sets of links are stronger than which other sets of links. Okay. And then we can check, then we can combine these you know, inequalities with the kind of restrictions you want to put, right? To see whether the intersection is empty or not. If it's not empty, it means that, you know, we can explain the data with, you know, 0 and 0.5. If it's empty, we cannot, right? We would need, this is one reason I really want us to get to data is that, I want to see precisely the kind of, I want to see this on data, you know, this kind of information we recover. How informative is this? I don't have a clue. It will depend on the data and the context, of course, but, you know, do we recover a lot of information and a lot of constraints on, you know, this altruistic relationship or not? At this stage, we're still thinking about this in abstract ways, but this is how I would do it. Yeah. Any other questions?
There are no other questions. So thank you, Yann. It was very interesting.